Hello students, in the last two classes we were studying about reactions of synthetic importance. In those classes we studied about oxidation and reduction reactions. In oxidation reactions we studied about opener reaction, it's also called opener oxidation reaction. In reduction reactions we studied about metal hydride reduction. In that reaction, we studied about two different reagents. One is sodium borohydride and the other one is a lithium aluminum hydride. Then we studied about Clemmensen reduction, Birch reduction and Wolff-Kishner reduction. In this class we will study about four different reactions. First one is in replacement reaction we are going to study Deakin reaction. In rearrangement reactions we are going to study Beckmann rearrangement reaction, then Smith's rearrangement reaction. In condensation reaction we are going to study Claisen-Smith's condensation. First one is a Deakin reaction. It's a replacement reaction. What is replacement reaction? It is nothing but the replacement of one group. As you can see here, replacement of one group. Here it is aldehydic group to another group, alcoholic group, or hydroxyl group, or the phenolic group. So that is a replacement reaction. So in this particular reaction, Deakin reaction, aldehyde or ketonic groups are getting converted to hydroxyl group. So it's an oxidation reaction, as I told you before. This reaction you can instead of replacement reaction you can put it into oxidation reaction. So it's the conversion of ortho or para hydroxy, this is at ortho position, to your phenyl aldehyde, ortho or para hydroxy or ortho amino phenyl aldehyde or ketone reacts with hydrogen peroxide in the presence of alkaline hydrogen peroxide in base to form benzene diol. So this is benzene and you have two alcohols here, so that is called diol. So you're going to get a benzene diol as the product. So what is the condition here for the initial product? So it should be phenyl aldehyde or ketone. So here it is aldehyde is shown, aldehyde product, or it can be even ketone. So attachment will be like, so if it is R over here instead of H, this H, so then it is a ketone. For this aldehydic or ketonic group, the hydroxyl group or amine group, you can even take the one with the amine group. This hydroxyl group or amine group should be at ortho position. So this is at ortho position, or this hydroxyl group, it can be at para position. Only such compounds can give this Deakin reaction. So let's look at the mechanism of this reaction. So as you know, we are taking hydrogen peroxide here in the presence of alkali, so we will take the sodium hydroxide here. This hydrogen peroxide will react with the sodium hydroxide and it's going to give this sodium peroxide, and this peroxide ion, it's going to get used further in the reaction. It will react with the initial product, so that is aldehyde over here, alpha hydroxy benzaldehyde. Here what happens, this carbonyl oxygen. Oxygen is electronegative. It's going to attract these bond electrons towards it because of the electronegativity, right? Then this is going to be partially negative, and this is going to be, because of that, this is going to be, this carbon is going to be partially positive. Because it is partially positive now, this peroxide ion is going to attack on this carbon, right? And this bond is going to get formed. And because this positive charge is like satisfied, neutralized, this electron which was towards electronegative oxygen will go completely go into that oxygen, and that will become negatively charged. Here, just observe the changes here. In this structure, this benzene ring is attached to the carbon, and in this structure it is attached to the oxygen, right? So this bond is going to shift to oxygen instead of this carbon. From carbon it is going to shift to the oxygen, and this shifting is called 1 2 1 2 1 2 aryl 1 2 aryl migration. So this is 1 2 aryl migration. Okay, now with this oxygen, that electron which is electronegative, it is going to come back to this bond, and it's going to form the same carbonyl bond over here. Okay, in between what will happen, this OH of this OH group or OH ion is going to get removed, right? So this is what the structure is going to form. Now this carbonyl oxygen again going to, you know, attract those electrons, and that is going to get negatively charged. This is going to get negatively charged, and this bond electron, because of this negative oxygen, right, it is going to attract towards that. As a whole, this whole thing will come out because of the break over here, and this will get negatively charged, and the formic acid is going to get formed. Because this is getting removed, formic acid is going to get formed, and the hydrogen from here is going to get shifted to this. This is electronegative here because of this negativity over here. This hydrogen is going to get shifted over here, and that will form that hydroxyl group over here, right? So that is how this aldehyde group is getting converted to this hydroxyl group, and you are going to get catechol from alpha hydroxy benzaldehyde. That is the reaction mechanism. Next is the application. First one, useful in the preparation of polyhydric phenols from naturally occurring hydroxyaldehydes. So example is orthovanillin. It is naturally occurring hydroxyaldehyde, and you are carrying out Deakin reaction. So you're going to get this product paragalol 1 monomethyl ether. So you're having that extra hydroxyl group over here. Second one, useful in the preparation of catechol from orthohydroxy or ortho-alkoxy aldehydes or ketones. Catechol used as a starting material in preparation of catechol. So, one of the substituent on the initial product, it should be like OH, right? So instead of OH, it can be even alkoxy, group like this. So that's what it says. Catechol, and this can be used in the preparation of catechol. We took the example of catechol itself, which you already know. So, and these catechols are the starting materials for the preparation of catechol amines. Third one, useful in the synthesis of glycol, which is a precursor of several flavorants. So glycol, which is a precursor of flavorants. Glycol is so this is glycol with the attachment OCH3 instead of OH. Right, these glycols are used um, as a precursor of several flavorants. So next is useful in the synthesis of indole quinolones. Indole quinolones are naturally occurring compounds and they can exhibit antibiotic, antifungal and anti-tumor activities. So quinolones so that is quinoline when OH group is attached, sorry, the double bond O or the carbonyl group is attached or the ketonic group is attached over there, then it is a quinolone. And you know the indole structure, the indole structure. When structure is attached like this, so that compound will be indole quinolones, and such compounds are very useful. So they exhibit antibiotic, antifungal, and anti-tumor activities. So Deakin reaction can be used in synthesis of such compounds. Alright, next is Smith's rearrangement reaction. Rearrangement. What is rearrangement? Rearrangement is the arrangement within the molecule with the little changes. So here it is, it involves migration of alkyl or aryl group with its bonding electrons from carbon to adjacent nitrogen. As you can see here, this carboxyl group is getting converted to amine group with only little of change, right? Instead of oxygen is replaced by nitrogen over here. That's what it says. And then this reaction involves addition of hydrozoic acid to carboxylic acid, aldehydes and ketones, as well as alcohols and olefins. So the reaction is between hydrozoic acid. This is hydrozoic acid, HN3. So further the structure can be expanded like this. So this is hydrozoic acid. So here carboxylic acid in this Smith's rearrangement, carboxylic acid, aldehydes, okay, ketones, ketones, even alcohols and olefins. They are going to react with the hydrozoic acid, and these are the different products you are going to get. Here you are going to, in case of carboxylic acid, you're going to get amine. In case of aldehyde, you're going to get cyanide. In case of ketone, you're going to get amide. So that is the reaction, and this reaction requires sulfuric acid. Instead of this sulfuric acid, you can even use Lewis acids. So Lewis acids are like aluminum trichloride, trichloride, or boron trifluoride. So these are Lewis acids. Instead of sulfuric acid, you can even use Lewis acids for this reaction. So as you can observe here, in case of a carboxylic acid, carbon dioxide is evolved and nitrogen is also evolved. So this is mainly a reaction of a carboxylic acid. You can see the common reactions with the carboxylic acid. And it is also olefins also can give this Smith's rearrangement reaction. Olefins are like straight chain carbon compounds. In straight chain, there will be one double bond somewhere in between. Such compounds are called olefins. Even these olefins give this Smith's rearrangement reaction. So what is the mechanism involved? So you're taking carboxylic acid here. So this is the carbonyl group. It has got that electronegative oxygen. So the electrons are going to shift towards this electronegative oxygen. So that will become partially negatively charged, and you are going using acid in this reaction, right? So this hydrogen is going to shift on to this. That is going to form the bond over there. So you're going to get a hydroxyl group over here, because these electrons got shifted over here for the bond formation over there. This carbon is going to get exposed, so this will become partially negative initially, then it will become partially positive, and then it will become positively charged. So that is carbonium ion over there, and this carbon is attacked by this hydrozoic acids. So this is positive over here, right? So this should be like little bit negative, and that is going to attract to this positively charged carbon, and this is what the bond formation. So after that, one molecule of water is going to get removed from here, right? And with this oxygen, the carbonyl group is going to form over here. So water molecule is getting removed, and carbonyl uh, bond is going to get formed over here. So look at the changes here. Right after that, what is going to happen is this from here, nitrogen is going to get removed. Nitrogen is going to get removed, and because of shift of these electrons over here for the removal of that nitrogen, this nitrogen is going to be positively charged, and because that is positively charged, these bond electrons are going to shift to the nitrogen, and that is this one is going to get separated. this one is going to get separated, and that proton is going to get removed, or the hydrogen ion is going to get removed, and meanwhile this um, alkyl group is going to go on to this nitrogen. It is going to go on to this nitrogen. This is what is formed, and it is isocyanate. Why is it isocyanate? It is actually CN here. It should be cyanate. No, actually the attachment is from this side, from NC, from NC. NC is attached to this R alkyl group, so it is isocyanate. So then a molecule of water getting added over here, molecule of water getting added over here, so this OH2 is going to get attached to this nitrogen, and this CO, the carbonyl CO, along with this oxygen of water is going to form the carbon dioxide, and with this rearrangement, so you are going to get amine. So because of the addition of water there, so you're going to get H2, and you're going to get the amine. So this is how the carboxylic acid is getting converted to amine in Smith's reaction. So next we will look at the applications. First one is the preparation of primary amine. So as you know, amines are formed from carboxylic acid. Here you are taking phenyl acetic acid, and from that benzyl amine is going to get formed. So this amine is a primary amine. So here there is H, hydrogen, and hydrogen, and there is only one attachment over here. So it is a primary amine. So primary amines can be formed from this Smith's rearrangement. Second application, preparation of alpha amino acids. So alpha amino acids are formed from this Smith's rearrangement, and we are taking acetoacetic ester. Even esters are going to take part in the Smith's rearrangement reaction. So you're using hydrochloric acid and sulfuric acid. The initial product is amide. So this is the product of Smith's rearrangement. Amide is going to form. We are going to continue this reaction. Okay, we are going to do acidic hydrolysis. We have to do the hydrolysis over here. Then only this alpha amino acid is going to form. So hydrolysis is going to take place. This is going to break like this. So you're going to get alcohol over here, ethyl alcohol, and from here you're going to get this alpha amino acid, and from this you are going to get acetic acid. This is alpha amino acid. Amino group is attached to the alpha carbon. This is alpha carbon to this acid, carboxylic group. So it is alpha amino acid. That is the second use of Smith's rearrangement reaction. Third one, used in the preparation of lactones. So what are lactones? So when CO, and then if you have like ether like, this particular group in the cycle, in the cyclic ring, then it is called ketone, right? So here in case of it is then it is called sorry, lactone. So in case of here it is forming caprolactam. When nitrogen is there instead of oxygen, then it is lactam. Otherwise it is just lactone. Right. So how it is, how we are going to get this caprolactam? So you have to take the cyclohexanone. Cyclohexanone, you have to react that with the um, hydroxylic acid in the presence of sulfuric acid. So you're going to get a caprolactam. This caprolactam is used in polymer industry. It is used to make polymer. It is used to make nylon. Nylon is a polymer, so it is used in that industry. So next we will study about Claisen-Smith's reaction. So we just studied Smith's reaction or Smith's rearrangement. So this is Claisen-Smith's reaction. It is also called Claisen reaction. So it's a condensation of aromatic aldehyde having alpha hydrogen with the aliphatic aldehyde. So it is the condensation reaction between aromatic aldehyde and aliphatic aldehyde. But there are certain conditions. So this aromatic aldehyde should have alpha hydrogen, and this aliphatic aldehyde, you can also take aliphatic ketone or ester. So that should have, the condition is that should have active hydrogen. Such compounds react together, or the condensation reaction is going to take place in the presence of a 10% alkaline solution. Okay, what is the product? The product is alpha beta unsaturated aldehydes or ketones. So let's go to the reaction. It says having alpha hydrogen, aromatic aldehyde should have alpha hydrogen, and aliphatic aldehyde should, aldehyde or ketone should have active hydrogen. Do you see the, so this is aromatic aldehyde, and this is aliphatic aldehyde. So these two should have, this should have alpha hydrogen, but I don't see alpha hydrogen over here. If we further go into reaction mechanism, this is actually alpha carbon, this is aromatic aldehyde. Okay, so this is actually alpha carbon over here. The hydrogen attached to it is alpha hydrogen, right? And the other condition is the aliphatic aldehyde should have active hydrogen. So actually this has got the active hydrogen. It is going to give out the this hydrogen. So compounds, aromatic compounds, which give out the attached to the which gives out the hydrogen attached to the carbon. So they are active hydrogens. So those hydrogens are active hydrogens, and this aliphatic aldehyde has got an active hydrogen. So the other thing is it is also a cross aldol condensation reaction. Aldol condensation reaction can occur in alkaline condition with only one kind of initial product. You can have aldehyde or ketone, just one kind of aldehyde or ketone. Here what is happening is we are taking two different aldehydes. One is aromatic aldehyde, the other one is aliphatic aldehyde. That's why it is called as cross aldol condensation. This is the reaction. The benzaldehyde reacts with the acetaldehyde in the presence of 10%. You are going to take a dilute alkaline um, solution here. So that is 10% sodium hydroxide. So you're going to get alpha beta. So this is alpha beta, and this is alpha and beta unsaturated, alpha beta unsaturated aldehyde. So you're going to get cinnamaldehyde here in this case. The same benzaldehyde, if you react that with the ketone, this is aldehyde, aliphatic aldehyde. This is aliphatic ketone. In the presence of 10% sodium hydroxide, you're going to get ketonic product, alpha beta unsaturated ketonic product, that is benza acetone. You are going to get benzyl acetone. So one more thing to be observed in this reaction, if you take a stronger alkali, it will cause Cannizzaro reaction. That is another aldehyde reaction. It can go to Cannizzaro reaction. That's why you have to take a dilute alkaline solution here. So here you are taking only 10% sodium hydroxide solution. So now what is the reaction mechanism involved? So first of all, this aliphatic aldehyde, so here it is acetaldehyde, it is going to give out this active hydrogen to this hydroxyl group. You have this hydroxyl group because of that sodium hydroxide, right? Because of sodium hydroxide you get this hydroxyl group, and this hydroxyl group will react with this active hydrogen, and you are going to get a molecule of water. So you are going to get this anion from this aliphatic aldehyde. This anion is going to react with the aromatic aldehyde. In this aromatic aldehyde, because of this electronegative carbonyl oxygen, the electrons are going to get shifted to that oxygen, right? Because that gets shifted over there, that is going to get a negatively charged. This carbon is going to get positively charged, right? This will be positively charged, and this anion is going to attack on this, and that is how this bond formation will occur over here. And because this oxygen is negative now, the hydrogen from the water, is going to attack on that, and that's how you get the OH group over here. And this OH minus from here is going to get this hydrogen, and that's how the water molecule is going to get formed. And because if this is going to go on to this OH, only the proton is going to go there, only H plus is going to go there, leaving one of the bonding electrons here. And because of this bonding electron, this bonding electron is going to shift to this carbon. So this is carbanion now. Now what will happen? One more molecule of water, let's take that out, this OH group, and this hydrogen, one of the hydrogen from here is again going to get removed as water, and because of that the double bond is going to form over here. So that's how you get this product, alpha beta unsaturated aldehyde. So here you are getting cinnamaldehyde from benzaldehyde and acetaldehyde. So this is the reaction mechanism. Applications, first one, used to synthesize alpha beta unsaturated carbon compounds. These alpha beta unsaturated carbon compounds are used as perfumes. These aromatic aldehydes, they give good odor. Okay, they are used in perfume industry. So in here, benzaldehyde reacts with the acetaldehyde, using 10% sodium hydroxide over here. So you're going to get the cinnamaldehyde. So we have come across this reaction. This cinnamaldehyde used in perfumes. Right, the second one used to synthesize natural products. Example, flavones, flavonol, piperine, and beta ionones. So these are natural products. These natural products can be prepared using Claisen-Smith's reaction. In here, so this is the product of a Claisen-Smith's reaction. You can see the alpha beta unsaturated bond over there, and you are going to continue this reaction using dimethyl ether and bromine. You are going to get this intermediary product. You have to further subject that to alcoholic potassium hydroxide, and you are going to get flavone, and flavone is a natural product, so you can use these products in another situations. So third one, Claisen-Smith's reaction used in the preparation of chalcones. So what are chalcones? So chalcones are or these chalcone rings can be seen in biological compounds. Chalcones and chalcone from central core of a variety of important biological compounds, and this chalcone is prepared from this Claisen-Smith's reaction. Actually, chalcone so this is chalcone structure. So you can see this structure in some of the biological compounds. So that is about Claisen-Smith's reaction. The last one is Beckmann rearrangement reaction. So it's a rearrangement reaction. It involves conversion of ketoxime to this is ketoxime to N substituted amide. So this is ketoxime, right? It's ketoximes are products of it is the product because of the reaction between ketone and hydroxylamine. So this looks like hydroxylamine, and this looks like a ketone, right? And if instead of one of the R is H, then it is aldoxime. So now it is ketoxime because of the two attached alkyl group to this carbon. It is ketoxime. If one alkyl group is hydrogen, then it is aldoxine. So reaction occurs in the presence of sulfuric acid, right? You have to take ether as a medium. Instead of sulfuric acid, you can take phosphorus pentachloride or phosphorus pentaoxide or pentoxide, or you can even take sulfonyl chloride. So what is the reaction mechanism involved? Ketoxine that reacts with this proton coming out from your acid, right? H2SO4. You can take H2SO4 here, right? This proton will react with this OH, and you're going to get OH plus. Meanwhile, this alkyl group is going to go on to this nitrogen, electronegative nitrogen, right? And this OH2 plus is going to be removed as water, right? You see the changes over here because this alkyl group is going to go on to this nitrogen. So you observe this structure over here, this structure. So here it is written NR, okay, NR. It is starting from this side. This is first, this is here, this is second, right? This is second. I'm writing it from this side, okay? And third one is, this is third one, carbon, right? The fourth one will be this alkyl group. So it is written the other way. So in between, this carbon is having only three bonds here. So you're going to have the positive charge over here. It's a carbonium ion or carbocation now, right? Now one molecule of water is going to get added over here to this carbonium ion, to this carbon. So it is going to get converted to OH2 plus. And from this OH2 plus, only H is going to removed, the proton is going to get removed, and that's how you get the OH bond over here. This OH bond, the alcoholic group, can get converted to ketonic group with the shift of this hydrogen, and this shift, this rearrangement is called tautomerism. Tautomers will have same um, molecular formula, right? But there is slight difference in the structure. So this is it is tautomerism, and because of the tautomerism, N substituted amide is going to form. So this is the amide, and this is how the ketoxine is get converted to N substituted amide in Beckmann rearrangement reaction. Let's look at the application of this reaction. It is used in the synthesis of isoquinoline. Isoquinoline is a heterocyclic compound. Here is the isoquinoline. So you have to take cinnamon dioxide for that. You have to take cinnamon dioxide, right? So here's the cinnamon dioxide. You have to treat with the phosphorus pentoxide. So you're going to get this intermediate product. It should be a double bond over here. So from here, the one molecule of water is getting removed, and you're going to get isoquinoline. So isoquinoline, you have come across this in uses. Isoquinoline for imidine and papaverine. Isoquinoline is the ring that is in those two structures. So next use is in the preparation of caprolactam. So here you can use this reaction for ring expansion. Here you have 6-membered ring, and that is going to get converted to 7-membered ring using a Beckmann rearrangement reaction. Here you are using phosphorus pentachloride. So the product is a caprolactam, which we came across before. There it is written in a different way. So anyway, so this is caprolactam. So this is, if this is O, that is, then it is lactone. So it is N over here. So it is called as caprolactam, and caprolactam is used in polymer industry to make nylon. All right, that ends this chapter. Thank you very much, and let me know if you have any questions.